Assalamu alaikum. Welcome back to my YouTube channel. And today we're going to discuss about calculating the polarizability and hyperpolarizability using Gaussian. I'm making this video because of a comment from a viewer who asked about how to calculate the polarizability and hyperpolarizability. So calculating both these polarizability and hyperpolarizability in Gaussian is actually very easy and straightforward. I'll just open this molecule. I've taken this test molecule. And however, the interpreting the results can require a bit of deeper understanding of the underlying physics of these phenomena. So I'll just try to describe how to calculate the polarizability and hyperpolarizability values of a molecule using Gaussian. So you know that the dipole moment of a molecule changes when it is placed under a static electric field, and this change can be calculated. And then definitely the molecular potential energy also changes with the influence of the external field. So we can calculate the polarizability and hyperpolarizability using the equations embedded in Gaussian. We'll take the example of this molecule. I have already optimized it. And because I optimized it on a good level of theory, I'll show you here. So we're not gonna do it again because it takes time. You can take any molecule, you can optimize it using your desired level of theory. I optimized it on a triple zeta basis set with the tight criteria, and I calculated the frequency as well. So if you look the vibrations, the molecule is a true minimum. There is no imaginary frequency, and it is optimized. So what I will do is I will just take this optimized molecule, I'll copy it, make a new, paste it with Control V, and then if I just calculate it, you can calculate it, the polarizability as a single point calculation, or you can combine it with the frequency calculation as well. So it's always good to have a look at Gaussian website where they describe each keyword with a bit of detail. So we're going to use the keyword polar. So I'll just write polar here, and then you can choose whatever method you want and the rest of the settings. So what this polar keyword will do, polar keyword requests that the dipole electric field polarizabilities and hyperpolarizabilities are to be computed. So in this, this keyword will calculate the polarizabilities and hyperpolarizabilities together. And it's written that you can combine it with frequencies calculations, but that is only available for the methods which have the analytical frequencies. So in the output, you will find the polarizabilities and hyperpolarizabilities values. And normally, polarizabilities and hyperpolarizabilities are calculated using static frequencies. So if you don't give any other keyword, it will be calculated using the static frequencies. But if you want to do a frequency dependent calculation, like you want to say, I want to calculate it on this frequency, then you can use the keyword CPHF is equal to R diffric, and then you can give the frequency after the molecular coordinate. So we'll come back to that. At the moment, we'll just do this, and you can use the DFT if you want, and I'll choose the functional this one, and then basis set I'll keep as def2 SVP. You can choose any other if you want. And then the empirical dispersion for dispersion correction. And you can also use the solvent. And I will use other and one for dioxanes because this molecule was calculated using the same solvent. So now I'll just edit and save this file. Click Edit, Save, and then give it a name. I'll just save it. So this is a big molecule. I'm going to run it on my high performance computer and then come back to you when the calculation is finished in a minute. Yeah, the calculation is finished now. And if you drag this output file, you can see this output file here. And if you go to results and summary, you can see that the polarizability and the hyperpolarizability values are given here. So you can find them and you can use them from here. So if you want to have a look at the output files, you can find the hyperpolarizability and then you can find the values in atomic units and other units as well. I will not go into more details about what are these values. You can search about them and you can also use the AI tools to discuss about it. I'll just tell you if you want to, for example, if you want to do it for a specific frequency, what we do is you just say CPHF is equal to RD fric in the input line, and then after the coordinates, leave one empty line and state the frequency in the atomic units here. So you can ask very easily, like I asked Copilot, how to convert atomic units to frequency and vice versa. For example, um, so it gave you the conversion factor from atomic units to hertz and from hertz to atomic units. So you can use the equation and convert your desired frequency in the atomic units and give to the Gaussian here. So if you save it and run this calculation, it will calculate the polarizabilities and hyperpolarizabilities using these frequencies instead of the defined static frequencies in Gaussian. So that was all about calculating the polarizability and hyperpolarizability using Gaussian. If you want to know more about it, you can search the internet and you can find some literature and discuss more about it. I'm basically not a physicist, that's why I'm not going into too much details, but I know how to calculate this, and that was asked in the comments, so that's why I made a video that you can definitely calculate hyperpolarizabilities using this software Gaussian, and then you can interpret it if you have a understanding of the concept. Thank you very much for watching. If you have any other questions or comments regarding computational chemistry or Gaussian software or Orca software, just post in the comment section and I'll try to get back to you as soon as possible. Thank you very much. Bye bye.